Hi, my name is Ed Killer, and I'm going to be talking to you about my Project 3, NetCDF on a sphere, in this short video. So what we're looking at is NetCDF on a sphere, where it has a couple different components in the interface. We have the left-hand side that has the ability to switch color modes, load different parameters. We can play an animation, and then we have this bottom section that shows the current location in the animation series, the min time step, and the max time step. In our center here, we have the sphere, which we can rotate around, and we can see the color mapping. So I can play an animation, and while this is loading the frames into memory, I can talk a little bit about the data. So the data comes from collaborators at Argonne National Laboratory, and what we're looking at is atmospheric data. In particular, we're looking at a parameter called TQ. TQ is the total water column. So you can think of it as if you take a ray from the surface of the Earth up into the atmosphere, it's integrated water, but along that ray. One of the interesting things about this dataset is it's an ultra-high simulation of atmospheric data. Typically, atmospheric simulations run at an order of 100 kilometers. For this particular simulation, they're interested in showing a 10-kilometer simulation of the atmosphere. And by doing this ultra-high resolution simulation, they're able to expose naturally occurring phenomena such as hurricanes, which we're seeing right now. So we're looking at the mid-Atlantic, and we can see a hurricane actually track up the coast toward the east coast of the United States. Now, although this is an ultra-high resolution simulation, the actual data that I'm using, I had to reduce in order to load it into the application. Originally, the data file that I had was 3 gigs. Each time step for this data file was 30 megs. If I wanted to play a very long animation, such as this, or longer, those numbers add up very quickly. It would be very difficult to load it into memory. So to subsample the data, I leveraged a tool called NCO, or NetCDF operators. And I was able to regrid the data to something easier to work with, and I reduced the time step files from 30 megs to 7 megs. And that's what we're looking at right now. So I can zoom in and you can start to see the lower resolution file. But by doing so, we have a real-time animation that actually can rotate. We can start to see how the weather systems are affected along the entire globe. So the idea behind this application, and the reason I wanted to view NetCDF on a sphere, is that typical NetCDF viewers are in 2D. And in 2D, you get a full, complete picture, but it's difficult to see how this system is related on a whole. And you don't get the full sense that the left-hand side of the screen is continuous to the right-hand side of the screen. And there's other applications, such as Science on a Sphere, which I have links to on my website, that show this type of atmospheric data actually projected on a sphere. And it really gives a compelling view of the world and the weather systems and how everything is related. And one weather system in one area affects the entire weather system as a whole. So my original plan for this project was to have this layered globe where you have atmospheric data layered with ocean data, layered with height map data of the world's oceans and the mountain regions, and then all textured using satellite data. Unfortunately, because wrangling the data proved to be so difficult and getting it into a form that was efficient enough to play animations, I wasn't able to completely achieve this goal. On the way to this, though, I wanted to take this TQ parameter and use it as cloud data. And I figured out a way of generating a color scheme where instead of specifically setting the colors for each value, I actually have a function that you define any number of RGB colors, and then you create a lookup table into that array, and it gives you your exact value. So this allows me to have things like this, where if I specify the correct parameters, such as a range between 46 and 93, I can extract out what looks like clouds, of dense clouds. And although this looks jaggy because of the resolution, I can then play an animation. And if I had the previous layers loaded in, you'd actually see a sphere, and you see the clouds over that sphere. Other parameters that I have access to are the sea level pressure. And I can just give you a view of what this actually looks like. Right now it's colored by red to white to blue. And this will give you a sense of what the parameter actually looks like. However, sea level pressure isn't the most compelling visualization from this data set. It really is the total water column.